Okay, so just go over the diagrams that I was talking about, just to make them a little better than I can draw them. This is the water diagram in terms of PE, pH, what we talked about. And then the sulfur diagram, again in terms of PE, pH. We calculated the SO4 2 minus to HS minus line on the diagram, and we showed that the H2S 0 stability field would be to the low pH side of the vertical line at, I think it was 6.99 pH, 6.99. And this just fills in the diagrams. So SO4 2 minus is stable all the way. It's stable all the way up to air. Of course, it's a stable form at the surface, except at very low pH, very acid conditions, and HSO4 minus is stable. And up here, S2 minus starts to become stable, but you need very, very low, high pH, very low hydrogen ion concentration to get to that point. This is just some interest. One of the reasons I first got interested in pH-PE diagrams was radioactive waste disposal, and this just shows you a diagram for uranium, and it shows that the solid uranium silicate is stable under very reducing conditions. And then, of course, these lines correspond to uranium of 10 to the minus 6 in solution. That's the normal convention. So at high pH and reducing conditions, this UOH5 minus is stable, and uranium is very soluble. And it's very soluble here under oxidizing conditions. This is oxidation state uranium, uranium 4 plus. This is oxidation state uranium 6 plus, and that's stable under more oxidizing conditions. So one of the problems with nuclear waste was the worry that uranium, which is in the fuel, is in the 4 plus oxidation state as uranium dioxide, UO2. That would dissolve under oxidizing conditions and produce these very stable soluble complexes of uranium 6 plus, like UO2 2 plus is obviously uranium is 6 plus. Each oxygen is 2 minus, so the whole thing is 2 plus. And a lot of energy has gone into creating these sorts of diagrams for uranium, plutonium, and other radioactive elements. And finally, I gave you this, or some part of this diagram to do in the practical. This is how it should look, pH-PE diagram. And the final thing I wanted to remind you was that PE here can be turned into EH, electrode potential, in volts. That's the units in volts, by multiplying by 0.059. So it goes to just over 1 volt in the stability field of water. Fe3 plus is stable here under very oxidizing conditions in solution and very acid conditions. I told you in the lecture that Fe3 plus wasn't very stable, and it's not. It needs very special oxidizing and acid-rich conditions. Fe2 plus, on the other hand, has a big stability field. And then if we go to oxidizing conditions at sort of moderate pH, moderate to high pH, we get solids like ferric hydroxide, FeOH3, or Fe2O3 becomes stable.